And with that, I am happy to introduce our first scientific talk of the day by Ivano Aiello from Mossland and Marine Mines.
Thank you. Thank you, Kirsten. And before I start, and before Kirsten starts the timer, I'd like to say a few words. Thank you, Kirsten. Thank you for organizing this amazing event. She's a force of nature, literally. She's an amazing scientist, a wonderful friend. I don't know what else to say. I mean, we're so thankful and lucky to have her in our community. So thank you. Okay. Well, here we are, a year and a half approximately after the Moss Landing battery fire. So today I'm going to be actually talking twice. I apologize in advance. You're going to hear from me a lot. The first part is about, the part one of the story, which is the evidence for coastal wetland deposition of cathode material in our coast loop. And my next slide is actually, again, this is a teamwork. And the team is a very broad team of different stakeholders. First of all, the Ember core group, wonderful scientists. I can't be, happier to work with such a group of talented scientists and friends. And also our students and field work, which have been fundamental. Lots of different collaborators across the spectrum. And finally, our funding sources. So Kirsten already introduced some of our funding sources. That gives me more time to actually talk about the science. But really, I want to make sure that everyone is acknowledged first, because I won't be standing here in front of you with these results without everybody's work. So the story for us starts before the fire, right? So Kirsten already introduced that. We're collaboratively working on a marsh restoration project. As part of this project, my component was to actually analyze soils for different aspects, geotechnical aspects, but also their composition, because we're trying to learn what is the best recipe to grow back healthy marshes. As part of this work in 2023, I set out to use a pretty new instrument, which is a portable X-ray fluorescence detector, which we'll talk about in detail a little bit later. And because of the well-known microzonation within wetland soils, which is that things change very rapidly at very shallow depth in wetlands in terms of the redox boundaries and such, we set out an experiment and actually a set of measurements near permanent benchmarks, so places where we can go back to over time by very much slicing the soil. So we start first measuring the surface and then the shallow subsurface. Actually, we went even deeper and we took cores and so on. And what we measure is the elemental composition of the soils. And so we had this great baseline data, which emphasized the usefulness of baseline monitoring. So having data from sites that can be disturbed is very important. So monitoring has a great value. I want to emphasize that. And the site, as you already saw in the previous slides, is very close to the Vistra Moss 300 battery facility, which caught on fire at the end of January 2025. So between 1 and 3 kilometers. Having worked here for many years, and I was here during the fire, we all got evacuated. And after you saw the timeline, after the EPA said the air quality is okay, thumbs up, go back to work. Indeed, we went back to work, which is we went back to our field sites just to look at the situation. And that was a few days after the fire. And it was clear that the signs of the burned material were everywhere. I mean, anyone could see it. There was soot on our boats, for instance, but there were also chunks, literally chunks of burned stuff all over the place. And some of them were actually pretty large. They were breaking up really easily. And I want to call your attention on some really interesting smearing here. There you can see this metallic smearing, which turned out to be transitional metals that then we measured also in the soil. And they were far away from the fire itself, and they were breaking up very easily. So there was the first evidence that maybe something happened after as a result of the fire. So as I mentioned earlier, we did have data before. So what we do, we look at the after, right? So we went back to some of our permanent transits. And we sit down in front of our computer, we plot our data, And this is one of those plots. So please bear with me. They're called bivariate plots. Is where we plot two variables next to each other. In this case here, the scale is logarithmic. So things increase logarithmically on both axes. And the two elements that you see plotted here, for a good reason, are cobalt and nickel. And they stood out. I mean, I really didn't know what I was looking for, but the number was so different from what I measured before that they really stood out. And the pre-baseline data give us a defined range of natural concentration of both elements. And I want to also call your attention on this header here. So only samples with quantifiable nickel and cobalt are plotted. So there were many known detects early on. In most places, there was no nickel and cobalt that I could detect. And this is right after the fire. And again, those are logarithmic scale changes. And as you can see, there was a new group, a new population from the same site, which had clearly much higher concentration than before. And also they were all grouped together along a line. And the basic science approach to this is that the two variables knew each other. Before they were varying at different rates without knowing what each other was doing, but now they are all along this 2-to-1 ratio between nickel and cobalt, which tells us that they were coming from the same place. That's a fundamental geochemical fingerprinting, which is used commonly in any type of scientific approach. And the displacement of this data point was significant, meaning that they jumped up several fold. So this was quite worrisome, and it required further sampling and to understand what was actually happening. And luckily, we have a beautiful instrument here that's called a scanning electron microscope, which allows us to look at very tiny things, very, very large, using an electron beam. And so I went back to the Alkan Slough, took some surface soils, put it under the microscope, and there you go. There were these little, actually quite pretty grapes-like features of those little tiny balls, which I've never seen before. And just to give you a sense, the scale here is 50 micron, 1 micron is 1,000th of a millimeter. So this is the average thickness of a hair. I don't know what it is because I don't have any, but I was told. And you can recognize some natural elements here. There's a little diatom here, some fibers. And I was curious. And as a scientist, the first thing you do is just Google it, right? I Google it, little metal balls and blah, blah, blah. And that's what I got. And I was like, oh, nickel, cobalt, manganese. Oh, that's what I'm seeing in my XRF data. And now look at that picture. I mean, this is exactly the stuff I was finding in the soil. And so, I connected the two dots. Didn't require a PhD for that. And it was clear that this was coming from the battery storage facility. And then I learned more. Actually, I did take classes in chemistry at school, and I know about batteries, and I know how they work, right? And so a rechargeable battery works as such. You have a cathode, which in lithium-ion batteries is often made of manganese, nickel, and cobalt oxides. And then you have an anode where the lithium is stored in the graphite. And when you discharge it, the lithium it becomes negative, the discharge, it migrates towards the cathode, and the electrons migrate the other way, and that's how you get energy. Then when you put back energy in it, you recharge it, and the battery dances back and forward. But much of the mass of a battery, lithium-ion battery, is actually made of those metals. So again, 2 + 2 or 1 + 1, 2, there were batteries stored in the fire, and they probably were destroyed, and some of those metals were ejected and ended up in a marsh about 1 to 3 kilometers away. That's the story, really. And it was pretty obvious from the start that there was a connection, but we explored this further, obviously. So we went back to these images here, and we start analyzing each single, well, not each, but those little tiny beads that I mentioned earlier. You can see they're actually really fascinating polycrystalline assemblages of nickel, manganese, and cobalt, because we can also measure the elemental composition of these micro spheres using the scanning electron microscope. So I think it's important to spend a couple slides or a couple minutes on the methods, because methods are, we know that you need the right tool for the right question. So you can measure anything. You can use a tape to measure the stable. You can also use a laser based instrument that will measure this table at the micron scale. So it really depends what you're doing and how you do it. And in this case here, I'd like to compare the two methods that we've been using for a study. One is X-ray fluorescence, which is really using X-ray, a beam of X-rays to fluoresce, which means making light, really, although it's an X-ray spectrum, to characterize the composition of the soil. This method is rapid. It's both based on field and a laboratory. So we have two instruments, we replicate the experiments, has a very high spatial coverage. In other words, you can measure a very small spatial variabilities within a few centimeters as well as miles away. And you can therefore take hundreds of measurements. And finally, it's surface sensitive because the penetration depth of the X-ray is very shallow, only a few tens of microns in soils. So that gives you a perfect understanding of what happens at the surface. As opposed to a very well and important type of instrumentation, which is ICP-MS, which is in which the elemental composition of sample is based on mass, relative mass. And this instrument has a very high analytical accuracy, is a laboratory-based instrument, and you work on bulk homogenized samples. So what you do, you take samples, you homogenize them, and then you subsample them. Unlike the X-ray fluorescence, works on much larger volumes, so it gives you a sense of the average composition of a certain sample. And has a very lower throughput because it's very expensive, it's very slow, and it is sensitive to sample strategy because of the homogenization that I mentioned earlier. Let me go to my next slide, because we did an experiment trying to understand where those metals were. And the experiment was based on measuring the relationship between, the relationship between the nickel, in this case here, content on the surface of the samples versus the nickel concentration once we homogenize the sample. Okay, so one thing is measuring the surface, the other one is taking the whole thing, drying it up, homogenizing, and remeasure. And that's what is in the bottom axis there. And on the y-axis, we measure the thickness of the samples right here. And what we found is that there is a relationship between the two. In other words, the thicker the sample, the lesser nickel concentration are measuring once we homogenize, which in science we call dilution, which is a pretty basic concept that's adopted across the board in natural sciences. And what we found is that the two can be replicated when we are within, 1 millimeter or 2, which means that, in other words, that most of the metals were concentrated in a very upper surface of the soil. That's what it tells us. And if you look at a sample, and you have my thumb as scale here, you can imagine how the metal-rich veneer was a very tiny deposit that the XRF detected very properly, while traditional samples, they are defined as shallow. Shallow is it's a word. So my colleague geodynamicists that study the Earth, they think the crust of the Earth is shallow. It's 30 kilometers, 100 kilometers. It depends what you mean by shallow, right? So in this case here, shallow is where the metals are. And if you take a typical EPA sample, 1 to 6 inches, then you'll be diluting a factor of 10 or 100. So that's to give you kind of a sense. So you saw this picture. Actually, this is the picture to the left is the before, right after the fire. Sorry, where we didn't know what we to find. That's right after. So you can tell how we really literally dressed up with PPE because we were really concerned about what we were breathing, of course. And so we continue monitoring the sites. And over time, in the next 3 months, we created a picture of the evolution of the metals on the surface of not just Esther Marsh that you see dashed here, but also a larger area across Esther Marsh. These are baseline data. Those are heat maps. In other words, the darker the color, the more the higher the concentration for the 3 elements. And this is right after the fire. You can see how they just light up in Esther Marsh, which is several kilometers away from the fire location, which means the bullseye of deposition of those metals wasn't the power plant, but it was actually further away from it. And finally, this is about 3 months after the fire, and we saw a decline in concentration. The same data set is represented here. Those are very complicated box plots, I apologize, but give you a sense, a temporal understanding of how the concentration of surface. This is what we measure at the surface. This is what we measure at the subsurface. So this is right after the fire. You can notice how the concentration of nickel in this case here, or is it nickel? Yeah, nickel jumped up to several thousand ppms, and which were much higher than the reference that we had before the fire, which is the dashed line. The subsurface, and by the subsurface I mean a few millimeters, didn't see anything. So again, this deposit were at the very surface of the soil. And then you can see how they declined in the months after the fire, with some interesting increases over time, but finally dramatically dropping off over the next year. The other interesting observation that I'd like to call your attention on is the scatter. So the scatter represents the fact that, again, the deposit wasn't a blanket, but was actually spotty. So there were places that were higher concentration, lower concentration, which is what you expect from an asphalt deposit. It wasn't an avalanche. It wasn't homogeneous. So you could have missed it if you were sampling here versus here, talking about 50 centimeters, so a few meters scale. You could have missed the whole thing. So the importance of replicated high resolution sampling. And this is what I just said. So finally, when we put together what we learned, there are, I think, 4 key lessons that we can learn. First of all, baseline data matter. So having the pre-fire data was essential, which tells us that whatever facility we are going to be building in the future, or current facility can actually be hazardous. It's very important to learn about the baseline, and it's not just soil, which are my favorite organisms, but also biota and water and so on. So understand the whole ecosystem before. So we have a before after. The other one is that the rapid response matters. So being out there the day after we were actually able to go there was fundamental, because you saw it was a pulse and the decline was very rapid. So we captured that pulse, and going there after months would have completely missed the big picture here. And the sampling strategy matters. So again, what's shallow? What do we do? Why do we do it? It has to have a purpose. So the right tools and the right approaches for the right questions. If you follow some predicament that were established for just general purposes, they might not apply for battery fires, for instance, where you have asphalt deposits. And finally, the importance of long-term monitoring, because then we can understand how the metals propagate and whether they've been retained by the system or not, something which we'll discuss together later more. So this is the end of my presentation, and I'm here for any questions you might have. Thank you.
We have plenty of time for questions. We're gonna today, throughout the day, take a couple from the room and then a couple from Zoom if there are some. So please.
Hi, Aiello. What's your opinion from all the research you've done can you elaborate a little bit further upon the effects of dilution in terms of getting an accurate picture of what came out of the flame?
Can you repeat just the gist of the question in case?
Yeah, so the question is about the effects of dilution on the big picture, you said. And I think it's, what I hope I was explaining earlier, which is that concentrations, when you measure concentration are relative to a mass or a volume. So therefore, the mass and volume that you sample or you analyze, because you can, in the case of ICP-MS, we sample, say, several grams of sediment, but then we homogenize it. Then we sample what is a quarter of a gram. So you're taking a parcel, a little tiny bit of a larger sample. So that instrument gives you an average over whatever thickness or volume you're sampling. It's obvious, as opposed to surface methods such as X-ray fluorescence or sampling, actually, that is only constrained to the very upper surface, which will give you a concentration relative to the thickness you have been measuring. So that's it. It's concentration. Again, those are not absolute numbers, they're relative numbers relative to the volume.
What are the biotic and abiotic mechanisms that contribute to a decline in concentration over time?
So the question is, what are the biotic and abiotic mechanisms that contribute to a decline over time? Sorry, I want to.
No, this is great. This is great. And so abiotic, definitely we think that the decline, and thank you actually for asking, because I forgot to mention that. I should have done that. So it rained after the fire, luckily. And so we think the runoff could have contributed to the removal of some of the surface concentrations although not everything, and also the tidal action, obviously, which was also another component that probably resuspended and removed some of the material. But there was also the solution in place, and you hear this part of the story in the next talk. So that's another way. Biotic will be, again, will be presented later. There will be the absorption of some of those metals in the tissues and organic parts of the invertebrates and filter feeders and so on.
We'll take a question from Zoom and then we'll return to the room.
Yeah, we have some upvotes on a similar question, asking what types of information is necessary to create a database for future evaluations, pre-development of a battery energy storage facility in case there's a failure of those. And they ask for suggestions for documentation and process for facilities near farmland or rural neighborhoods as well.
Excellent question. And I think that
loud enough.
I think it was loud enough. So what type of data should be collected before near a facility? And I think we're going to have a panel discussion that probably will touch some of these points, but it's good to say that, well, as we are going to show, data on soil composition on different distances from the facility itself. So we will learn from other accidents is that if potential contaminants are entrained by a small plume, the plume travels. Those things are very tiny. I'll show you in my next talk how tiny they are and how far they can travel. So a logarithmically spaced sampling from away from the facility and water, both surface water as well as groundwater is also very important. And then some fundamental sentinel organisms. That's what we are also learning together. There are organisms that are more likely to capture the signal. So maybe we can learn how to use those organisms in the future to establish baseline, but also to intervene in case another accident happens.
Your chart you spoke to about the initial concentration very high, and then it went lower over time. And you spoke to that as dissipation. Isn't it also an example or a symptom of persistence in that chart? Because there was heavy metals that still showed up, I thought.
Yeah.
That chart.
Yeah, I can go back to it's right here. Yeah, really good point. Thank you. Yeah, so the even though the decline, as you mentioned, the concentration for the next year was still statistically higher than the baseline concentration. However, the decline is obvious, and which means, but I'm not saying that they disappeared. Obviously, they just moved away from the surface soil. Also, the other thing that I want to call your attention on is that the subsurface probably was picking up some of those metals. You can see there's a clear increase. So some of it could have moved downward again, a few millimeters because of bioturbation, for instance, or shear just transfer through the pore space. And also there's speciation, which is the metal starts shedding, which something that you'll learn in the next talk. So I don't want to give up too much of the information. But there's also, I mean, they're chemically reactive. They didn't stay there as little metal balls for too long. That's the other thing, right?
We still have time for questions. We'll take another from Zoom.
There's a related one on Zoom. So while you're on this plot, someone asks, did the pulses or small increases at certain sample dates over time coincide with a storm or otherwise stirring up of the sediments?
Can you say that again? Sorry.
Like, do you know the small increases or pulses that happened at later sample dates?
Yeah.
Coincided with storms or other types of events that might stir up?
Right.
sediments?
So thank you. So there are, as I mentioned earlier, there are the curve, the decay curve is not the curve. There are actually there's variability, there's variance on that, and actually those points that you see with the higher values, those are the salt pans in Esther Marsh. So those are places where much of the water after tidal ingression, after high tides, rather than draining back, evaporates. And so we think that probably what happens is that the water, as it evaporates, concentrates the metal in little salty, nasty, metal-rich ponds. And we found that to be pretty significant. So in other words, the metal is going to have the way to drain because there's no connection with the main tidal channel. And you probably have seen that when you go out there, after high tide, there are little pockets of water standing there. So that's what we think, because there's also more salt. when we find more metals. So that's a possible interpretation. That's a really good point.
Emily?
You mentioned that there was kind of a sporadic deposition of like, it wasn't evenly distributed after the fire. Scattered. And, that therefore there's a need for a lot of sampling. And I was just curious, if you can describe what differences perhaps between your sampling and say the EPA sampling? Or can you describe at what level would you need to sample to make sure to catch that random scattering?
Absolutely. Yeah. And, I can speak I don't know if EPA samples soil directly, but I can tell you that our approach, even before the fire, was to account first of a small scale variability. So what you do, you work around those benchmarks and you do multiple measurements around, because the first thing you need to know, when you're comparing things, the first question is, what is the the local variability? So replicates within a few really centimeters from each other, and then increase the scale, right? And the other thing is just use your eyes, because when you see debris on the ground, that's clearly wasn't there before, and it smells like burned stuff. So most likely it's coming from a fire. Again, you don't require PhDs for that. But then based on that, you observe how this debris is fragmenting and it's getting smaller and smaller. So eventually there's a whole range of scales also in terms of this fire-related deposit. But I would say that for baseline studies as well as post-fire studies, you want to first resolve things at the very small scale locally, and then increase the scale. I mean, those are pretty traditional environmental analysis methods that we didn't come up with any of that. I mean, this is really the regular approach. And having benchmarks, it's so fundamental. We do have GPS now that bring you back to the millimeter, but having visual reference actually is a fundamental thing. So our transits are fantastic for that point. I hope this answers your question.
So I don't think you can answer this, but I'd like you
Thank you, Rick.
to speculate on it. What you have is sampling in discrete locations and changes and concentrations over time. So can you tell me how you might go about answering the question, what's the difference between a low concentration everywhere in the slough versus high concentrations in some places in the slough?
In case Zoom couldn't hear the question, it's about sort of the spatial scale of variation, and that one could have on the one hand sort of a uniform concentration low everywhere, or the same average concentration but distributed patchily, high some places, low others. Is that
Right, because it appears from your data that the metals are moving from your sample sites.
Excellent. Excellent.
So that could.
Excellent question. Yes.
So that's the question. I don't know.
Yeah, no, this is actually really good. Thank you, Rick. Obviously, you're a very bright mind, because yes, I mean, and that's something that we are discussing currently, which is you're talking about redistribution of the metals after the deposition, right? So you have the first measurement that I would argue probably captured in situ deposition, the primary deposition, although there was wind, so things have moved around. But then eventually some of the monitoring data that show this lowering across the scale might be due to just the fact that the metals are being reshuffled rather than, I would say that's this great hypothesis. Now, how would I test it? I don't know. I need to think more about it, but it's a good point. So again, just to emphasize what Rick just said. So we found the spotty initial really high, really low values after deposition, but then eventually things start lowering down, but still in the average high. So that's possibly because the metals just moved around because of the tides, because of the rain. So they didn't just wash out. They also homogenize across the soil. Yeah, thank you.
Can you step onto the stage and answer another question there? And allow Max to be, yes, Max.
Yeah. I thought you want me to be taller.
We have time for another question.
Taller than Max.
And then we'll move on, but we'll give Max a chance to get started. Jacob.
Yeah.
Are there components of estuarine or marsh soil that might be particularly reactive to these specific metals or maybe just in estuaries more broadly, like that hold these metals more particularly than others?
Absolutely. So the question is whether there are soils or components in estuaries, and I would say habitats that might be more receptive. So the first thing, obviously, we didn't look at plants yet, meaning this is all the bare soil. So we skipped the whole canopy on top. So just think about underestimates, because we didn't look at the elephant in the room, which is the stuff that was actually catching probably most of it, although some of the marsh soils where I worked were bare, so there was no plants. So to answer your question, we had actually initially one hypothesis, which still I think is valuable, which is the fact that the physical properties of the soil during the deposition might have characterized their ability to retain the particles, because they were wetter soil, which were freshly inundated. It could have been more sticky, literally more sticky. So like the clay-rich soil could be more conducive to concentrating and retaining those particles, even when the wind is blowing, so they kind of hold on to them. And then plants, marsh plants, because we know that very well, especially if they interact with wind, the stuff tends to be trapped by the canopy. So absolutely.
Yeah, I'm also thinking about like reactions to the metals
That
in addition to the metals themselves.
Yes, so that would be and we know that cobalt and nickel have slightly different behavior in different oxidizing and reducing environments. And we're actually studying that. We are about to set out a series of experiments, which I'll talk about in a few minutes. So thank you. You're actually setting up my next talk. I appreciate that.
Thank you so much.
Thank you.
Ivano.
Thank you.